All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully, you guys are doing well. We're still in the middle of a section, even though we're going to start something different. But let's actually just jump in. Where are we? Make sure I can see the chat here. Yeah, so we've come a long way. We did a bunch of stuff with limits. Maybe I should go back a little bit more. Quick recap. So limits, remember, this is notation. We say the limit as x approaches a of f of x equals L. What that is this is what the y value gets close to as our x gets close to this value, right? And getting close means getting close. It means that you don't need to be at the point. Limit doesn't care. Whether it's filled in or not is irrelevant. You just talk about getting close. And getting close means arbitrarily close. You should be able to get as close as you want. There should be no gap between you and the point when it comes to the function. So that's basically what our limit was. We looked at some examples. As we get close to 2 from the left or the right, we realize that the y value went closer to 5. Here was another example where we weren't defined at 2, but the limit doesn't care. We realize that as we get closer to from the left or the right, the y value approached 4, so the answer was 4. Then we saw this one, which was strange, where we approach from the right. It seems that the y values are approaching 7. We approach from the left. It seems that the y values are approaching 0. So we're like, is it 0 or is it 7, right? Civil war, right? And so now it turns out that in that case where there's a disagreement does not exist. We can't do this, right? We need to agree. And so this also brought up the notion of one-sided limits. So the idea is, yeah, sometimes our definition of a limit doesn't strictly exist or make sense, but the point of a limit is to kind of talk about the y value, right? So clearly I know what's going on with the y value, it just doesn't fit my definition. So we invented these new things so we can talk about the y value one side at a time. Of course, we realize that the overall limit will only exist if both one-sided limits exist and agree. So we spoke about that. And I spoke about the fact that, you have to be able to get arbitrarily close, can't have a gap, all that good stuff. There are various scenarios for existence and non-existence of limits and their one-sided limits. But one thing is for certain, unless both one-sided limits exist and agree, the overall limit won't exist. Okay. Then we jumped into a bunch of examples. These guys taught us about limits at infinity and infinite limits. And these guys we used to help us learn to apply strategy. So that's what we went into, right? So we learned about limits at infinity and infinite limits. Basically, this was the following. If you take a limit and your answer is infinite, positive or negative, it means you have a limit, an infinite limit. If your inputs are approaching infinity or negative infinity, we call that a limit at infinity. You can be both. For example, this guy is an infinite limit at infinity, right? It's an infinite limit because the output is infinity. It's a limit at infinity because the input is approaching infinity. Okay, we also looked at properties. Limits had some very nice properties. There were 6 main ones. Limit of a constant is just a constant. We can factor constants in and out of limits. So limit of a constant times a function is the constant times the limit of the function. Limits distribute across sums. So the limit of a sum is the sum of the limits. Limits also distribute across products, which is crazy. Almost nothing does both of those things. Nothing off the top of my head right now, but I think prior to calculus, there's nothing that we've seen that does both of those things, right? So nothing distributes both across sums and products, but the limit does. Very nice. Also distributes across divisions as long as you're not dividing by 0. That is, always a thing we're watching out for. Limits can also move in and out of powers. This includes radicals. So I can move a limit symbol inside a radical, outside a radical. And yeah, it's all golden. Limits have very, very nice properties. Almost anything you think you should be able to do with a limit, you can do, as long as you're obeying the overall definition of a limit. So that's pretty cool. Limits are very nice. However, when we are faced with a bunch of weird looking problems, Even though limits are very nice and we have rules for computing them, it's kind of hard to know when to do which. So that's why I gave you guys a bunch of strategies. So this is how we attack every limit problem, no matter what. A random problem shows up on a limit. A random limit problem shows up on a test, a quiz, homework, whatever. This is how you think about it. First thing, you try to plug in. Chances are, if that works, that's the answer. Technically speaking, we have to be continuous for this to work. I'll talk about continuity today, but pretty much any function that you'll see that you can plug in and get an answer, it's going to be continuous for you anyway. You have to be careful with piecewise functions and things of that sort. But virtually, while limits don't care about anything being plugged in, if on both sides you connect and you can actually plug in, then plugging in is actually the quickest way to get to the answer. So it's always the first thing you try. It's the easiest thing. And if it works, you're done. So you might as well try that first. If you can't plug in, the second thing you're going to try is, can I simplify the plugin? So you have an example like this, where I couldn't plug in the 2. So I was like, what can I do? Can't plug in the 2 because Jhevon's going to kill me if I put a 0 in the denominator. So what I try to do is I try to simplify so I can plug in the 2. All right, and then we can get an answer that way. Step 3 was a special technique. We know one already, which is actually step 6, to know about the behaviors of functions. And I'll teach you guys another one right after I finish the recap. So if you don't see a special technique, then you can use a graph or a table of values. So you pretty much let X approach the thing you care about. For example, if we're approaching 0, you approach it from above and below, inch closer and closer to it, and then you see how the Y value reacts. In this case, we can see that both sides were going to infinity, and so the answer was infinity, right? Because they both agree, left and right. The other thing, and of course, we already know how to do it from the graph, right? So you just look at the picture. We've done a bunch of things like that, right? So step 6 is to actually look at the functions that are involved. Sometimes, specifically when you're taking limits at infinity, you know that as X goes off to infinity, different functions behave different ways. Exponentials are huge compared to polynomials. Polynomials are huge compared to exponentials in the sense that the smaller guys are effectively 0 compared to the bigger guys. So once you know that, you can actually get a good intuition for all sorts of things. So you see a limit like this, you don't have to do a plug-in because you can't plug in infinity. You also can't simplify. You don't know how to graph that. Wouldn't want to do a table of values, right? And it's just a weird thing. It's going to infinity over infinity. As X goes to infinity, X to the 7 goes to infinity. As X goes to infinity, E to the X plus 1 goes to infinity. But hey, not all infinities are created equal. In some sense, this infinity gets to infinity faster than this infinity because of this rule, right? We're comparing an exponential and a polynomial. So the bottom is going to overwhelm the top. We have a huge denominator and a small numerator. So that limit is 0. We call this bottom heavy. If things were reversed, of course, the opposite would be true. It's like I have infinity on the top and a very small number close to 0 on the bottom, right? You have a huge numerator, small denominator, you get a big number. So I can know that that limit is infinity without any calculations, no graphs, no tables, nothing. I can see what kind of functions are involved and I know how my functions behave and I just can apply that. And then, yeah, I can just tell you the answer. And as far as showing your work is concerned, you just write down bottom heavy or top heavy. And I will take that as you know that I know that you know that this is what you're applying, right? Okay, then we went into our bunch of examples and boom. So we spent a lot of time computing those, applying our limit rules. So we know that, hey, if you can plug in, you plug in. For this one, we couldn't plug in, we simplified, we got the answer. Some comments on notations, very important. Keep writing the limit symbol until you actually take the limit. Make sure you're using the limit symbol correctly. Don't put the equal sign in between the limit and your function, things of that sort. You remove the limit once you actually plug in the numbers and you're taking the limit. We talked about that as well. Here, we couldn't plug in. We simplified to see if we could plug in. We still couldn't plug in. So now we have to do something else. What are our options? Special techniques. I don't know any right now. So what I could do is I could graph, which is the easier option here, or I could do a table of values. Either way, we end up with DNE. So here, plug in. yeah, we want to do that, but we can't because we would divide by 0. So now we go, okay, step 2, simplify. But what does it mean to simplify that? Well, I need to know what the absolute value is. I need to understand my notation. So we broke it apart. Once we broke it up, we could then simplify then, and then it's clear that it does not exist, right? You could also graph. The graph would look like this. And again, it's obvious that it does not exist. Here was one, couldn't plug in because division by 0. Simplify, how do you simplify? Well, multiply and divide by the conjugate, of course. That is something that we know. And then we got somewhere where we could plug in. Awesome. This one is leading into what I'm going to start talking about today. So we had this guy, and I mentioned when we are going to a limit at infinity, this only applies to limits at infinity. Okay, so once I'm doing that, what we can do is find the highest power in the denominator, which in this case was x to the 4th, and then I can just divide every term by x to the 4th in the top and the bottom. What's going to happen is that all of these guys are going to have, you're going to notice that the polynomial in the bottom is larger than the polynomial in the top, and polynomials outgrow polynomials. That's another behavior of functions kind of thing. So an x cubed compared to an x squared, the x cubed is going to be huge compared to the x squared. The x squared is effectively going to be 0 as we're going off to infinity. That's what this takes advantage of. You'll notice that everyone gives you 0 except this guy in the denominator. So you get 0 over 2, which is 0. Again, this is a limit at infinity. I have a bunch of polynomials. So again, find the biggest power in the denominator, divide everybody by that. In this case, you realize we ended up with a 6x squared right here, some fractions right here that go off to 0, and a 2 in the bottom. Of course, 6x squared as x goes off to infinity is going to be infinite, and there's a negative sign right here. So that goes off to negative infinity over 2, which is negative infinity. This one, again, very similar, limit at infinity. It's a ratio of polynomials, what we call a rational function, because it's not rash, it thinks through its decisions. We divide top and bottom by the highest power in the denominator. Play the same trick again. Sorry, we're down here. Play the same trick again. In this case, we ended up with a number over a number, and that was the answer, right? So now, basically what I'm going to tell you is another special technique, which is a shortcut for this thing. Turns out that these 3 problems fall into a very special category of which we can apply a special technique. So I want you guys to know that we can do that and notice how you can do that. So that was a very quick recap. We actually worked through all that, but limits are kind of, like I said, weird for people seeing them for the first time. So I'm going to recap everything we do for a few lectures. Okay. Hopefully you followed all that. I went through very fast, but we actually went through it together very slowly through the class. So hopefully that quick, down and dirty crash course recap was enough. All right, so let's get to the special techniques, shortcuts, because ain't nobody got time for all of this, right? So of course you could write all of this, and of course I would give you full credit, but comes at an opportunity cost. You're in a test, you don't have time, the clock is running out. You don't want to waste time writing all this out when there's a much shorter way. You just don't. It's just not the wise decision. If you blank out on the special technique, then yeah, and you remember this, then you have no choice. You do it, but not ideal. So what I'm going to do now is I'm going to show you how to actually get these guys a lot faster. As it turns out, the above illustrate all possible cases that can occur in a special situation. So there's a special technique hidden here, and that's what I'm going to tell you right now. So this is a special technique for limits at infinity of rational functions. Okay. Now, common mistake. I need you to remember this. Very important. This is a special technique, not just a special technique. It is a special technique for limits at infinity of rational functions. In the past, I've seen students try to apply this technique when they don't have a limit at infinity. It's like, what am I going to do? 0 credit. I can't, like, everything you did was wrong, right? So the technique I'm going to give you applies in this special situation. That's why it's called a special technique. It applies in special situations. When you see something like this, that's a limit at infinity of a rational function, right? Or this, that's a limit at infinity of a rational function. That's a limit at infinity of a rational function. If instead of infinity, I had 2 right here, this does not apply. It only applies to limits at infinity of rational functions. Okay? Sometimes you show people stuff and it's really cool. They just want to do it all the time. It's like, oh, that's amazing. That's like, oh, right? They just want to do it all the time. You have to be careful. This is math. The devil is in the details. You can only use this in a special situation. That's why it's a special technique. It's not a general method. Okay. Once we have that down, now we can talk about it. So recall, first, let's make sure we understand the words. What is a rational function? This is a ratio, that's where the word rational comes from, of polynomials, right? So this means it looks like a function p of x over q of x, where q of x, of course, is not 0, and p of x, q of x are polynomials. Yeah. Now, hopefully you remember what a polynomial is. I don't want to describe that. It's a constant times x to some whole number of powers being added together. Okay, so you should know, like, these guys are polynomials, right? 4 plus x minus x cubed, all those stuff, right? Constant times x to some whole number of powers, right? If you have an x to the half or a radical x, it's not a rational function anymore. However, you can slightly generalize this technique to those cases. I'll talk about that later. But that's what a rational function is. So this technique applies to limits of the form. Okay, so here is when you know you can use this technique, you need to be looking at something like this. Remember, I've been telling you guys, the rules are your templates. If it doesn't fit the template, don't use the rule. Okay, so here's what it needs to look like. It needs to look like a limit as x approaches plus or minus infinity. You can use it for either, but it needs to be infinite. It can't be any random number. If it could be a random number, I would have put an a here, but I'm not putting an a there. I'm putting infinity, right? So it looks like limit as x approaches plus or minus infinity of something that looks like this, p of x over q of x, where p, q are polynomials, right? So you have a fraction, polynomial on top, polynomial on the bottom, and the x is going off to plus infinity or minus infinity. It turns out it's actually very easy to know what's going to happen, and all possible things that can happen are illustrated by these examples that I picked here. It turns out that this represents all possible cases. There are 3 general cases that can happen in this situation, and yeah, I know what I'm doing, so I picked those examples to kind of illustrate that. So here are the 3 possible scenarios. You'll notice that one of them, the answer was 0. It turns out that this is always going to be one of the cases. So there are going to be 3 possible cases. One case is you'll get the answer 0. When will you get the answer 0? Whenever the degree of Q is larger than the degree of P. Maybe I should remind you of that. Also recall the degree of a polynomial p of x, written dg of p, is the highest power of x that appears. And of course, appearing means it has a non-zero coefficient. Okay, so example, if I have p of x equals 2 plus 3x minus 4x squared, that is degree 2. We call that guy a quadratic. If I have p of x equals 2x to the 7th minus 3x squared plus 5, that is degree 7. Right? So essentially, if the highest power of x is in the q, notice that q is in the bottom. If the highest power is in the bottom, it will always be 0. Don't waste your time doing any calculations. Notice up here, if I looked at the highest power in the bottom, it was degree 4. If I looked at the highest power in the top, that's degree 3. 4 is bigger than 3. The higher power is in the bottom, right? That means the answer is going to be 0. I don't need any calculations. I don't need to be dividing stuff. Now, the reason why this is what I'm showing you, right? If you divide by the highest power in the denominator, top and bottom, it turns out that because this is the higher power, all the powers in the top will be x to some negative power. And so that's going to go off to 0. That's always going to happen. You don't have to do it and check it every time. So at this point, we call this bottom heavy. Right? The bottom is bigger than the top. It outclasses the top. Right? Bottom heavy is not an official term, so not official term. Okay. Don't go talking to some other random math professor. Hey, professor, bottom heavy, right? What? Like, you can't do that. Bottom heavy, this is just me to you guys saying you are allowed to write the phrase bottom heavy on a test, and that's just something between us. I know that you know what you're doing, right? So I know that you don't have to show all this. If you write bottom heavy, I know that you know that in the background, that's what's going on, and this would be the answer, right? So that's how you're gonna show your work. Just write the phrase bottom heavy. Hey, so on a test, you could say this equals 0 because it's bottom heavy, right? And you don't have to write all of this, right? And so that's what I'm saying there. So, but it's just between us. Like, that's not like a math term or anything. Okay, so that's one possibility. Here's another possibility. The answer can be infinite. Now, it might be plus or minus infinity. You have to just pay attention to the signs. Right? So the old rule does apply, like, oh, if you have a negative divided by a positive, then the answer should be negative. Or if you have a positive divided by a negative, the answer should be negative. If you have a negative divided by a negative, the answer should be positive. That's what I mean, right? So if you know your x is going to a negative thing and your p is going to be a negative value and this is going to be a positive value, then you know the answer you should pick is a negative infinity, right? So that's what I mean. Just be careful of the signs. And you should also remember, when you plug in a negative number into an odd power, the result is negative, right? So things like that I expect you to know. But yeah, so just be careful of the signs to know which is which, but it's going to be some sort of infinity in this particular case. This is, of course, whenever the opposite happens. The degree of p is larger than the degree of Q. So again, that's the top, that's the bottom. So if the larger one is in the top, it's going to be infinite, right? So you can call this top heavy. Again, not an official term. Right? Now, if we go back to our example, you're going to notice here, the highest power on top was 5. The highest power on the bottom was 3. So you look at that and you immediately know it's some sort of infinity. It's either going to be plus or minus infinity. How do I know which is which? So now I pay attention. Okay, here my x is approaching negative infinity. So let me do that. Here my x is approaching negative infinity. If I plug in negative infinity into x into the fifth, that's going to give me a negative infinity. Then I'm going to multiply that by a negative 6. So overall now the top is a positive infinity. If I take that negative into this guy, it's negative, multiplied by a plus 2, it's negative. So overall, I have a positive divided by a negative, and that's how I know it's a negative infinity, right? Because I watched the signs, right? So I didn't just choose negative infinity at random. I looked in detail what all the sign operations would give me, and negative infinity is what won, right? So that's what I meant by pay attention to the signs. And then there's another possibility, right? Which is the last and final possibility. It can approach the leading coefficient of the numerator divided by the leading coefficient of denominator. Okay. And this happens whenever the powers are equal. Degree of P equals Q. That's the only other case we haven't looked at, right? And this, you can call this a ratio of leading coefficients. Okay. And this is what happened. Oh, by the way, do we remember what a leading coefficient is? Maybe that's something else I should talk about, right? As I mentioned, definitions are important. You need to know what all, so you scribble this somewhere. You don't have to scribble it here specifically, but you should also recall what leading coefficient is. Recall the leading coefficient, guy in the lead. As you are going to realize, it's not always the guy in the lead technically. It's the guy in the lead if you arrange things from highest power to lowest power, but it's just the coefficient of the highest power. So the leading coefficient of a polynomial is the coefficient of the x to the highest power. Right? So if I wanted to take these same two examples, right? So we know the degrees, the degree of the top one is 2, the degree of the bottom one is 7. What is the leading coefficient? Well, the leading coefficient is -4. He's the guy that is the coefficient of the guy with the highest power. This one has leading coefficient is 2. That's the guy who's the coefficient of the guy with the highest power. Notice that in the first example, the -4 isn't the one in the lead technically, right? He's the guy that ended up last place, right? But that's not what lead means. Lead means if I arranged it in descending power order, that would be the guy in the lead, right? So that's what you need to know for leading coefficient. So leading coefficient is the coefficient of the guy with the highest power. Degree is the highest power. So this 2 here is coming from there, and this 7 here is coming from there. So when you're looking at the degree, it's the power. When you're looking at the leading coefficient, it's the coefficient of the guy with the highest power. Okay, so make sure you know that. So let's talk about this part. So the answer is going to be the leading coefficient of the numerator divided by the leading coefficient of the denominator. You will notice that that is what happened in this last example. Here, I notice the highest power on top is 3, highest power on bottom is 3. The degree is 3 in both the top and bottom. They have equal degrees. So what that means is I need to find the leading coefficients. The leading coefficient in the top is the 17. The leading coefficient in the bottom is -2. So what is the answer? 17 over -2, right? So, and that's all possible cases. There's never going to be any other situation for this type of limit. So you see these guys, there's only one of 3 things that they could be. And what I will take the opportunity at this point to do is to maybe redo them, but redo them in the cool way. Maybe I'll make them a little bigger since so now we're going to do them again, and we're going to do them super quick. And you're going to be like, what? How do we do it so fast? Knowledge. Okay, here. I'm going to redo all these guys. So this guy, move it under here. This guy, yeah. What happens? What's happening there? Stop messing up, computer. This guy, move it under here. Okay, so let's do this again, but now like a pro, right? So I see this limit on an exam, right? Show up. Hey, I notice that there is an infinity here, and these guys are a ratio of polynomials. So what do? I immediately identify the guy with the highest power in the top and bottom, right? Ignore everyone else. They do not matter. Look at the guys with the highest power. Who has the highest power? The highest power is in the bottom. What happens when the highest power is in the bottom? 0, bottom heavy, done. Fully worked out answer. Right? Now, I think that's fair. That I'm not forcing you to do this. I know a lot of math teachers who actually, I want you to know really what's going on and you have to write it up. Okay, so me, I'm not that crazy. I will allow you to take shortcuts. The only thing is you have to tell me something. I want to know you didn't just plug it into a calculator and got the answer. I need to know that you actually have a reason for the answer. So you must write this. That's the trade-off, right? Either you do all of this or you write a sentence. I think the sentence is going to be preferable, but you must write this. Or I will consider it as not showing work. Right? Which I think is fair. It's a fair trade-off, in my opinion, right? Saves you a lot of time. All you have to do is write down a couple words, but you have to write something. If I give you this on a test and you just write down 0, I don't know if you cheated or just plugged it into a calculator or used Wolfram Alpha. I don't know. When you write, this is the answer because it's bottom heavy. Now I know, oh, this person was looking, I at least know that they know that the highest power is on the bottom, right? See this example, right? Again, hey, it's a limit at infinity, right? So now I focus on the highest powers, ignore everyone else. They do not matter. Now I realize that the highest power is on the top, right? Which means this is going to be plus or minus infinity, right? I immediately know that. Now, which is it? So what I can do is I can just go here, okay. If I have -6 times negative infinity to the 5, well, that's, this is negative and that's negative, so this is a positive, okay? And in the denominator, I would have 2 times a negative infinity cubed. Okay, so that's going to be negative in the, that one. And so that means that gives you a negative, which tells me that this is the right sign that I want to pick, right? Not that one. So, and I mean, you don't have to write out this line, but you just immediately now just write down negative infinity, right? But you have to, like I said, pay attention to the signs, right? To know, should you take the positive or the negative infinity? So now you know it's negative infinity. How do I know? It's top heavy, right? But you know, this is what I mean by pay attention to the signs. Okay. Last one. Have this. What do I do? Plug in? Can't do it. Can I simplify? What is the graph of this? You shouldn't be thinking any of that. You spot that this is an infinity and you have a ratio of polynomials, right? So zoom in on the biggest guys. Degree, the highest power on the top and bottom is the same. All I now look for is the ratio of the coefficients. There's a 17 here, there's a -2 there. -17/2, ratio of leading coefficients. Done. That's the answer. Okay. So meanwhile, all the kids are doing this. You're like a pro. You've been around. You've seen some stuff. You've lived some life. You have some time under your belt. You're like, I know how this story is going to play out, kid. You know, when I was your age, I used to worry about all this stuff that I didn't have to worry about. But now I know this is what's going to happen, man. I'm going to tell you. Let me. Well, old people don't know anything. You don't understand what it's like to be my age, right? And eventually they go through life and they learn that that's what's going on, but whatever. Okay, I'm just an old man complaining about me trying to educate these kids, tell them what's up. No one listens to me though. All right. That actually took a lot longer than I thought, but I think it was worth it. It's very important for you to understand exactly what's going on and why you're doing things the way you're doing them. Do I want to start continuity? Probably not. Yeah, I'll leave continuity for next class. I guess what I can do at this point maybe is just review some important ideas. So that's the basics of limits. Or those. We will do more with them. We will do more with limits. Don't worry. But from a computationalist perspective, you know 99% of the things that you should already know for this class. I'm going to tell you a 1% thing a little later in the semester that is actually going to be pretty cool. We will do more later. But some important takeaways. So I would say, make sure you know what a limit is and what it cares about. Limits care about getting close, not about being at a point, right? So it's about getting close, not about being there. You don't need the value to be filled in. You don't need to, the function doesn't need to make sense at the point where you're taking the limit. That's not what the limit is about, right? So the limit is the y value you get close to, right? You don't have to get there as your x value gets close to some a. And again, gets close to. Again, you don't have to actually be able to get there. That's very important. What else? So yeah, your f of a may not be defined, but the limit as you approach a of the function can still exist, right? So I want you to have that idea in your head. What else do I want to make sure? A limit only exists if both one-sided limits exist and agree, right? So sometimes you have to check the one-sided limits. There are common situations in which you would have to do this. Of course, common situations, not all situations. You have to, I taught you enough. I went at length explaining everything conceptually. So hopefully you'll know how to navigate things. Even if I don't never tell you about some scenario, when you find yourself in that scenario, you'll know how to navigate it. But just as a rule of thumb, let's say, so if you realize that you have a situation where you should have done this, but I didn't specifically mention it, don't blame me. I gave you more than enough to know. But some common situations, if you have absolute values. And limit is at where they switch from positive to negative. Where the insides, the absolute value is never going to switch from positive to negative. Where the inside switches from positive to negative. You definitely want to look at one side at a time. So if you have an absolute value of x and you're taking a limit as x approaches 0, then it means on the right side, your x is x, while on the left side, your x is negative x. So it's going to totally change the function that you're looking at. You need to make sure you're looking at one side at a time. Obviously, piecewise functions. And you're taking a limit where it is broken up. Generally, you can consider this generally when you just find yourself in a weird situation. You're just in a weird situation and you just want to tread carefully to make sure you're not making a mistake. You'd probably want to just consider one side at a time. It might be easier for you to conceptualize when you're in a weird situation and want to tread carefully. Okay. And where are we? So we did an example. Yeah, so like here with this piecewise function. So remember, I gave you the thing that, hey, if you can plug in, just plug in, right? So you're going to be like, oh, when x equals 2, that's the function. And of course, I can plug in 2, and that makes sense. It's not divided by 0. So I'll just plug in 2 here, and the answer is 0, right? No, it's not, because it's a piecewise function. And at 2 is where it's broken up. So the whole plug-in idea isn't good enough anymore. Now you have to worry about, yeah, I could plug in the top, but officially the limit doesn't actually care whether or not I could plug in. This thing changes whether I'm on the left side or the right side of 2. I need to tread carefully. I need to look at the one-sided limits, right? So these are just some concepts I want you to have in mind. To keep in mind. What else? Is there anything else I want to tell you? I think that's it. Know the strategies. Know the strategies. Follow them in order. Know the properties, right? What you can do with limits, how you can distribute them and things of that sort, how you can actually just do math computations with them, right? So the student who can take a limit test and get A+ like a boss, finish the test in half the time, that student is the student who's aware of all of this, right? They know their properties and they know the strategies. They know what a limit is really about, so they don't get like distracted by plugging in stuff when they shouldn't be plugging in. They know a limit is about getting close. They know the function doesn't have to be defined. They know that there are certain situations in which they just take it easy, go one side at a time. Once you know that and you know all the strategies that I'm telling you, this limits is nothing. If you don't, limits is going to be very hard and confusing. I can tell you that for sure. But I gave you enough to have you guys not have to struggle, you know, like the old man trying to give his kids what he never had. So, you know, don't grow up to be like me, kids. I struggled a lot when I was going through math at your age. You know, everyone just told me, hey, you should just know this. I'm telling you guys what you need to know specifically so you can actually go through, live your life to the fullest. And that's it for now. Next time we'll start continuity, which it is going to involve us talking about limits, but it's like we're going to use the fact that we know how to compute limits to do other stuff and to determine certain nice properties of functions that we're going to need for calculus. We'll stop there today. As I mentioned in an email, I had to cancel office hours for today because I have some engagements coming soon that I could not get out of. So if you want to set up an office hour with me at some other point before the next scheduled office hour, you should just email me. Until then, have a good weekend. I will see you guys in the next one. Ciao.